Lesson 14, X marks spot, solving systems graphically. So a system of equations, that's when you have two lines on the same grid. And we say X marks the spot because where the lines intersect, that's the solution. So, and that's really it. I mean, like with a system of equation where the two lines meet and you're asked to find the solution, you write whatever relation or ordered pair that is. That's your answer. So we got some learning objectives. One is we're going to learn the definition of a system of equation. So for this class, that's just two systems. Or by systems, we just mean linear functions or equations on one grid. If you go far enough, you can have as many equations as you can fathom on one grid, but for this course, just two systems. There's going to be three possible outcomes. We'll talk about what those three are. I'm not going to tell you now. If I tell you everything at the beginning, you won't want to listen to the whole thing. And then we're going to figure out how to write the solution, and I sort of give that away. It's just an ordered pair or relation. You need to know, and you can do them. You got to be able to graph a linear equation like we have here. And for fun, I'm going to go ahead and write this equation because you'll need to know how to do that. Your b is 6. Your slope is, here's a good lattice point. So we 2, 1, 2, 3, 1, 2, 3. The guy's walking uphill, so our slope is 3 over 2 x plus 6. You've got to be able to write an equation or take an equation and graph it. You can do that because we've done it together. You got to know your slope and your intercept. Whoops, we just did that. And then you need to know how to go from standard form to slope-intercept. So you need to know how to take an equation like this and put it in slope-intercept. Well, this one here, you just subtract 3x from both sides. And now that's in slope-intercept. But just to make sure that we're clear on it, we're going to graph an equation. You always start at b. In this case, b is -4. We don't know what our slope is. Looks like our slope would be 2 over 1. So you'd go up 1, 2 over 1. So we went up 1. I'm sorry, we went up 2 over 1. And then you connect the dots. So here's one for you to try on your own. So graph this one. So you start at -8. Then you're going to notice your slope is negative. So when you draw your line, the person's got to be walking downhill, and your rise over your run is 3, 4. So imagine you probably already put a dot here. And what was our slope? That's right, it's -3, 4. So you go up 1, 2, 3. And then what's our run? That's right, 4. Do we go right or left? Which way, right or left, will make this line slant downward? That's right, if you go left, 1, 2, 3, and then you connect the dots with this. You got your equation. So if you can do that, you're going to be good for this lesson. So there's some new terms, and they really may not be new terms, but we're going to add some stuff to them because, you know, in grade school, you learn parallel lines they never touch. But now we're going to add, they had the same slopes or, you know, the same steepness. And that's the reason they don't touch, is because they go on through infinity with the same rate of change, the same steepness, the same slope. Perpendicular lines, well, you may remember they form right angles. But a new thing is when you multiply their slopes, they equal -1. That's what we call negative reciprocal. Reciprocal means it's just two products that equal 1. So 1/2 and 2, they're reciprocals because when you multiply them together, you get 1. So any reciprocal, and reciprocal is just another way of saying you're going to multiply two things to get 1. Anytime you do that, it's reciprocal. So a negative reciprocal would be that with the negative sign. Inconsistent lines, these are just another word for parallel lines that have the same slope. Well, we also say these lines have no solution because they never touch. Infinite solutions, well, these are lines that are multiples of each other. So when you graph them, and we've seen this, right? We've had a couple of equations, we've graphed it, and we got the same line. Well, it's because they're multiples of each other. It's the same line, just written in a different way. So when you have a system of equations and you have the same line on top of each other, like you have here, we call that infinite solutions because it touches everywhere. And then one solution, that's just your intersection. X marks the spot. So what is a solution of equations? Well, we have here, we got two equations. So we have two equations of graph on one grid where they intersect. In this case, 1, -1, that's the solution. Right here, this one has a solution. You write your solution as an ordered pair. So here, x looks like it's -1, y is 0. And that's it. A lot of people think systems of equations complicated. It's not. It's only complicated or hard for people who don't understand the foundational material. No solution, we say they're inconsistent. The lines are parallel, they have the same slope. And then infinite solutions. It's the same equation. So like this little red line I'm drawing has the same equation as that blue line. So it's the same equation, it's just in different forms. So, if you had like 3x plus y is equal to 4, well, that's the same thing as y is equal to -3x plus 4. These equations have the same line. They're the same value, they're the same input-output ratio, but they're just written differently. And that's all this is. It's infinite solutions. So just one more time, one solution, and these are our three possibilities. So with the systems of equations, with two equations in this, like in this course, you're either going to have one solution, which is where they intersect. They're going to be parallel lines, or no solution. And you could do n/s, or it's the same line, which means it's infinite solutions. Okay, let's look at this one. What is the solution of the systems? Now, you don't have to know the equations, and I think this is where sometimes people get caught up because they're like, well, I don't know what the equations of these lines are. We can find them, but we don't have to, so we're not going to. All we're going to do is just look at this graph and see where they intersect. So here, I'm going to go on my x-axis. I counted over 1, so I know my x is 1. I'm going to count up to where they intersect. So that's 1, 2, 3, 4, 5. And I'm just going to double check that. 1, 2, 3, 4, 5. And you just write it as a relation or ordered pair. In this case, it's 1, 5. So our solution here is 1, 5. Our next one here, what's the solution? Where do these lines intersect? Do they intersect? Will they intersect? So it doesn't look like they will ever intersect. So what do we call them? That's right. No solution. They're parallel lines. You may be asked, and not in this course, but like on the ACT, SAT, a standardized test, you may have a question like, prove these lines are perpendicular. So what you would do is you would find your slope, which is both cases. It's 2 over 1. So your slope here is 2. And you would say these lines are parallel because they have the same slope. By definition, lines with the same slope is parallel. So that's pretty straightforward. I'm not going to ask you that, but that is a common test question. Last one here, just to recap our 3 possibilities. What's the solution? And this confuses people when they see this because they're like, there's only one line. So if there's only one line, what do we know? That's right, it's the same value. It's just we could have 2 equations written in different ways. So we say there's infinite solutions because everywhere on that graph they touch. Now we have this one. So what's the solution? Well, first thing we got to do is we got to graph. So this is where graphing is important. You could always make a table. So we're going to make a table for this first one. So when x is 0, y is 2. When x is 1, 2 times 1 is 2. That's 2. And when x is 3, 2 times 3 is 6. So, you know, that's one option. Or you could, I always like to use slope-intercept because here I'd start at 0. How far up do I go? That's right, 1, 2. How far over do I run? That's right, 1, and it's positive. So a person's walking uphill, which is why we get a graph that looks like it's going uphill. We're going to double check it. Intersects at 0. My slope is 1, 2, and it's positive, so it's going up. Now let's do the same thing for line 2. We're going to go to 4. We're going to look at my slope. So that's a negative slope. Is it going to slope upwards or downwards? Is the person walking uphill or downhill? So right, they're walking downhill. So when I go here, I want to go down 1, 2, because that's my rise. I'm rising 2, which is rise is how far you're moving on the y-axis, and then I'm going to move 1 on the x-axis. I chose to go right because I want these lines to go downhill. If I rose 2, went over 1, 1, 2, 1, I'm still on that same line. One reason I went down is because I wanted to meet that line there, just because it's going to help me visualize what's happening. But when you draw that line, we'll get something that looks like this. So now our solution is whatever point that is. So it looks like we go over how far? It looks like, yeah, that's right. Somebody said 1. How far up do we go? That's right, 2. So our point here is, our solution is 1, 2. So the solution here is 1, 2. So on some of the problems in your work, you'll be given a graph and you just look where X marks the spot. And it's just that easy. Other times you'll be given a system like this. You have to graph it, and then you have to look for where those lines intersect. And in this course, if your numbers aren't perfect, every solution is going to be a lattice point. So just whatever's closest should be right for you. So here, we've got standard form. I always like to put these in y-intercept because a lot of times if you did your x and y intercepts in some of the problems, they're not going to be good lattice points. But whenever you put it in slope-intercept, you always get a good point. So just as a way to remind you what to do here, remember this from the previous lesson, but we're going to go ahead and solve for y. So first thing we want to do is we want to subtract 2x, and we subtract 2x from both sides of the equation. So that's going to give us negative y is equal to negative 2x. So this negative y it's not by itself, right? Because it's the same thing as negative 1 is equal to negative 2x, which is why here we're dividing both sides by negative 2. So now we got y is equal to 2x, and that's something that we can graph. And some people, myself included, I always like to add that plus 0 when I'm graphing, because that reminds me to start here at the y-intercept. And how far up do I go? So I rise 2. Now am I going to run right or left? And keep in mind, that's a positive slope. So when I go up 2, and I'm hanging out right here, does right or left make that line go up? That's right, right makes that line go up. So we want that line to go up. So our line should look like this. I'm going to just verify it's positive, it's going up. I'm going to double check my 0, double check my slope. It's 2 over 1, so we're good. Now we're going to do the same thing for this equation. We're going to solve for y. So you may want to pause the video because you want to subtract 2x from both sides. You want to get that solved for y. So go ahead and stop the video, get your work done. And if you want, you can go ahead and graph it before you come back. So when we solve this equation, we subtract 2x, like we did here, and that gives us y is equal to negative 2x minus 2x plus 4. Finally, we're left with y is equal to negative 2x plus 4. So once again, you had 2x plus y is equal to 4. Subtract 2x from both sides. You get y is equal to negative 2x plus 4. So we start on 4. 1, 2, 3, 4. How far down, up or down do we go? That's right, we rise 2. For fun, I'm going to go up 2. Then how am I moving right or left to make this line go down? That's right, I'm moving left because you want our line to go down. We want our person walking downhill. If I went down 1, 2 over 1, I had to get the same thing. So what's more important than going up or down is the direction you run in determining whether or not your line is going to slant up or down. When we graph this, what do we get? What's this point here? That's right, that's 1, 2. That's the beauty of math. You can have the same equations and still wind up with the same answer. So these equations here, they were our first example. We put them in standard form, or I did. When I solved them for y, it was the same thing. In your work, that's not always going to happen. And let's see here. So that's it. I mean, that's all there is to this lesson. So you'll either do one or two things. You'll be given a graph, and you look where the X marks the spot. And where X marks the spot's your answer. So it could be anywhere. Probably big thing here is just to watch your sign. So like I made this dot here, that's negative 5, 4. But anywhere two lines meet, well, they should have met at that dot. Try it again. There we go. So like this would be negative 8. I'm sorry. That would be negative 6, negative 8. So anywhere where those lines meet, or you graph the equation like we did here, and then you look for where they meet. Just to recap, before we turn you loose on your online practice, all we're doing is we're just plotting two equations on a graph. We have three possibilities. There's infinite solutions, no solution, or one solution. So here, one solution. If I did this, if we had the same line on top of each other, it's infinite. And then if they were parallel, it'd be no solution. So once again, no solutions, infinite solutions, one solution. This should be enough to get you through your work. If you need help, just let me know.